Every algorithm we design operates within a boundary defined by undecidability. The halting problem asks whether a general algorithm exists that can determine for any arbitrary program and any input if that program will eventually finish executing or run forever in an infinite loop. This is not merely a difficult engineering challenge, it is a fundamental impossibility proven by mathematical logic. We formalize this question using the Turing Machine model, the foundational abstract machine representing all computable processes. If such a decision procedure, which we call H, existed, it would revolutionize computer science, allowing us to debug all software automatically and solve complex theoretical problems instantly. The proof that H cannot exist relies entirely on a rigorous application of proof by contradiction, demonstrating that the assumption of H's existence leads to a logical paradox. A Turing machine M is defined by its finite set of states, tape alphabet, and transition function. The input W is the initial configuration of the tape. The hypothetical halting decider H must accept two inputs, the description of the machine M and the input W. H must always terminate itself, producing a binary output, 1 if M halts on W, and 0 if M loops infinitely on W. Crucially, H must function correctly for every possible combination of M and W. If H itself failed to halt, it would not be a decider. The existence of H implies that the set of all halting programs is recursively enumerable, meaning we could list them, but the proof will show that this set is not recursive, meaning no algorithm can definitively decide membership for all cases.
To derive the contradiction, we must construct a specific auxiliary machine, D, based on the assumed existence of H. D takes a single input, which is the description of another Turing machine, M. D incorporates H internally. When D receives M, it passes M twice to H, effectively asking H the question, does machine M halt when given its own description M as input? This self-referential input is the key mechanism borrowed from Cantor's diagonalization argument. D is designed to behave oppositely to the output provided by H. If H predicts halting, D must loop. If H predicts looping, D must halt. Let us precisely define the operational steps of D. D starts by invoking H with the pair M, M. Since H is assumed to be a total function, H must return either 1 or 0. If H returns 1, indicating that M halts on input M, D enters an infinite loop immediately. This ensures D does not halt. Conversely, if H returns 0, indicating that M loops infinitely on input M, D immediately halts and terminates its execution. This construction ensures that D's halting behavior is always the inverse of what H predicts for the specific self-referential input M, M. D is a valid finite Turing machine description, constructed entirely from existing components and the hypothetical H. The contradiction arises when we feed the description of the machine D itself as the input to D. We analyze the execution of D when processing its own code, D, D. Since D is a Turing machine, its description is a valid input for any other Turing machine, including D itself. We must now determine whether D halts when given D as input. This requires consulting the assumed halting decider H, which is embedded within D. D calls H with the input pair D, D. H must return a definitive answer regarding the halting status of D on input D.
We examine the two mutually exclusive possibilities for the output of H on D, D. Case 1. Assume H returns 1, meaning H predicts that D halts on input D. According to the definition of D, if H returns 1, D must enter an infinite loop. Therefore, if H predicts D halts, D actually loops. This is a direct contradiction of H's prediction. Case 2. Assume H returns 0, meaning H predicts that D loops infinitely on input D. According to the definition of D, if H returns 0, D must immediately halt. Therefore, if H predicts D loops, D actually halts. This is also a direct contradiction of H's prediction. Both possible outcomes of the assumed decider H lead to a logical impossibility. If H predicts halting, D loops. If H predicts looping, D halts. This means that D halts on input D if and only if D loops infinitely on input D. Since a program cannot simultaneously halt and loop infinitely, the behavior of D is logically inconsistent with the prediction made by H. The machine D, constructed using H, cannot exist if H exists. Since D is a valid construction based on the assumption of H, the only possible conclusion is that the initial assumption must be false. The halting decider H cannot exist. The halting problem is therefore undecidable. This proof establishes a fundamental limit on the power of computation, demonstrating that there are well-defined specific questions about programs that no algorithm can universally answer. This result is robust across all equivalent models of computation, including lambda calculus and register machines, due to the Church-Turing thesis. The undecidability of the halting problem implies the undecidability of many other related problems, such as determining if a program ever outputs a specific value, or if two programs are functionally equivalent.
The undecidability of the halting problem means that automated verification tools cannot guarantee the termination of all arbitrary programs. Practical compilers and static analysis tools must rely on heuristics or restrict the class of programs they analyze, such as ensuring loop bounds are always finite. This limitation is why software testing remains essential. We cannot simply run a universal termination checker. Furthermore, the halting problem is located at the first level of the arithmetic hierarchy, specifically the sigma 1 level, meaning it is recursively enumerable but not recursive. This places it precisely at the boundary between solvable and unsolvable computational problems. The technique of diagonalization used in this proof is a powerful tool in mathematical logic, also used to prove that the real numbers are uncountable. In computability theory, the halting problem serves as the canonical example of an undecidable problem. Its proof structure is generalized by Rice's theorem, which states that any non-trivial property of the language recognized by a Turing machine is undecidable. A property is non-trivial if it is neither true for all recursively enumerable languages nor false for all of them. Understanding the halting problem is essential for grasping the inherent limitations of formal systems and algorithmic processes.